When you calculate the electric or magnetic fields from Hertzian dipole, they have, I'm not going to write down the full expression because it kind of takes a long time and it's, anyway, but they have components that are proportional to 1 over r, but they also have components that are proportional to 1 over r squared and 1 over r cubed. However, most of the time we can ignore these 1 over r squared and 1 over r cubed terms. The reason for that is, if you want to talk about the amount of power radiated by a source, the total power, I mean, what you do is you calculate E cross H. You do 1/2, and you take the real part, which means you have to make room and erase your 1/2. And that gives you the time average Poynting vector. And then you integrate it over a surface that surrounds your source. And usually it's a sphere, but it could really be anything, that as long as it fully encloses the source. The total radiated power then is just this closed surface integral of, oh, and now I'm using S for two things, so we're going to name the surface A instead of S, of the Poynting vector dotted with, we're going to make it dA, the differential surface element. And if you do that, then you get the total power radiated by this thing. Now, what if we choose a sphere of radius r? And then we let r approach infinity. That Poynting vector is going to have some terms that are 1 over r squared, because that's going to be the contributions of the E and H, both proportional to 1 over r. But it's also going to have some terms that are proportional to 1 over r cubed, or 1 over r to the 4th, and a few other things. But as you let r go to infinity, all of these other terms are going to stop contributing to the outcome of this power integral here, because they decay faster than the surface area of the sphere increases. The easiest way to look at this is to remember that for a sphere, the differential surface element is r squared sine theta d theta d phi. So if you multiply a over r squared, where a is just some constant I made up, and you multiply that by r squared, you get a constant value of a. But if you multiply a constant divided by r cubed times r squared, you get b over r, and then if you let r go to infinity, these terms go to 0. These terms, and the product of these terms, product with dA, goes to 0. as r goes to infinity. So only 1 over r terms of the electric and magnetic fields contribute to radiated power when you're far away. And fittingly, we call those the far fields. If you're in the far field, then the electric field has only a theta component, and the theta component term that counts is, and this is for a Hertzian dipole, J I naught L K eta over 4 pi times sine theta times e to the minus j k r over r. And the only magnetic field term for a Hertzian dipole is h phi, and that is approximately J I naught L K over 4 pi sine theta e to the minus j k r over r. The interesting thing to note about these is that they obey all of the rules for plane waves. So you've got E theta over H phi, look, it's equal to eta. And if you cross E with H, you get something that is in the K direction. But here, your propagation vector is r hat directed. So the energy from your source, this is a symbol for an antenna. The energy from your source, the power from your source, that's represented by your pointing vector, which is also known as a radiated power density, is coming out radially away from the antenna. You can even use those simplified equations for the relationships between the electric and magnetic field vectors as though this is a plane wave, even though it's not. Just as a reminder, those are that H is equal to 1 over eta unit vector in the propagation direction crossed with E, and the electric field is equal to minus eta times the unit vector in the propagation direction crossed with H. Except here, these unit vectors in the propagation direction, those are r hat, the radial spherical vector. I've got one more thing to talk about with the pointing vector and radiated power. So when we're talking about antennas, the pointing vector is also called the radiated power density. And in general, for every antenna, the pointing vector has a particular form. And it's because the electric field always has a particular form, right? For any antenna, the electric field can be written like this: some function of angle that captures the phase information, the amplitude information, and the vector direction of the field times e to the minus j k r over r. Then, also true for any antenna, the pointing vector is equal to the magnitude of that amplitude and phase and angle function divided by 2 eta r squared. That's the radiated power density. But if it's so easy to separate out the distance dependence from the angle dependence of an antenna, it's also useful to talk about the radiation intensity. So we define the radiation intensity to be r squared times the magnitude of the pointing vector. Oh, and it occurs to me that this pointing vector up here didn't have a vector attached to it. It's r-directed. And that radiation intensity works out to be the magnitude squared of that amplitude function for the electric field divided by 2 eta. And this is the amount of radiation from this antenna per square angle rather than per unit area. So it has only the angular dependence of this thing. And this is most of the time what people are referring to when they're talking about the radiation pattern. When they're talking about the radiation pattern of an antenna, they're talking about, in some form, this radiation intensity. It's power per unit angle, and it's normalized to remove the R dependence.